from RUSTOM MODY PE. Anybody know what that is? That's for Petroleum Engineer. And RUSTOM is the Vice President for Technical Excellence at Baker Hughes, which is acquired by GE. And we went out and visited Rusty's toolbox. So the first time I realized I needed to work with the oil and gas guys was really when I met a guy called Bill Klein. Bill actually worked for ExxonMobil, was one of the founders of Pumps and Pipes. And their labs were about 4 miles from here. He had about $1 billion a year research budget and about 900 PhDs working with him. So I don't know if you can beat that, but I figured these are guys that we really need to work with. And so RUSTOM gets to see all the new concepts. And the way the oil and gas works, is companies work, is they talk about upstream technology, which is kind of from the platform down the hall, which is kind of where all the kind of stuff is that we're kind of interested in, versus, you know, the downstream, which is from the platform to refineries and things. So RUSTOM gets oversight in a lot of these things. His wife also happens to work here at Methodist Hospital in pathology, so he's kind of part of the family. Thank you for doing this, RUSTOM.
Good morning. I want to first thank Dr. Lumsden for inviting me to speak to such a distinguished audience. And this might be a little change of pace for you guys. I mean, heard a lot of things this morning, it was quite impressive. And I think I kind of will connect with what you guys are listening this morning, especially coming from the energy sector. I got a couple of just a basic introduction of who we are as a company, just a one slide. Our current industry challenges, and this is all going to be tied together, so bear with me. The other thing is, I'm going to talk about what is innovation. You know, I just came back from Midland, Odessa. Before that, I was in San Diego at a Brazil-US Innovation Summit. And the term innovation is used very loosely. People use it like giving out candies. And I want to talk about the definition of innovation. To get a better perspective of when we say innovation, is what it really means. And why formation imaging for us in the energy industry is so critical. And then I'm going to talk about some borehole imaging technologies. Should not surprise you guys because we have leveraged a lot of these technologies from different industries, but we apply it differently. And then I'm going to wrap it up with questions. So Baker Hughes has been a company around for about 115 years as an energy service company. And just about 6 months back, we merged with GE, oil and gas, to be a full stream company, which is upstream, midstream, and downstream. I'll talk about just the difference between those terms, like Dr. Lumsden said. And we are pretty much a global powerhouse when it comes in terms of bringing technology to the oil and gas industry. When we talk about the term upstream, it's all about technology that is used to recover reserves from the oil well. That's upstream. Midstream is all about transportation. And there's a lot of imaging technologies in the pipeline transportation business also that we participate and we develop. I'm not going to talk about that. And then downstream is basically refining. So Baker Hughes GE is the only company right now that is involved in the both upstream, midstream, and downstream part of the business. And the reason we had this merger is to bring digitization in the oil patch, which we are still lagging behind. That's enough of Baker Hughes GE. In our industry, over the last 4 years, since 2014, it's been pretty critical. We've been really struggling with the price of oil. And the reason I bring this slide up is, irrespective of price of oil, is we still have to develop technology to make sure our customers can still make money at this level. Because in 2014, at a national conference, at $107 a barrel, the biggest gripe by most of the CEOs was cost of doing business. And the cost of doing business increases dramatically at this price of oil. We could develop technology to improve productivity. So, you know, Lumsden talked about the budget we have. Actually, it's not $1 billion, it's close to $500 million, just a little change. But I always get questions about how do you invest money in what projects you work on? And over the last 37 years in industry, I've come with a simple application which applies to every industry, and especially in innovative companies, is really whatever you develop, it better create value in the marketplace. It's as simple as that. If you're not creating value for your clients, you're not going to be successful. The second most important thing is it has to reduce the overall risk of using the technology. If whatever you develop technology is, if it increases the value for your clients, but it's risky to use, it's not going to be adapted. And the third and most important thing is it has to increase efficiency. In other words, compared to your previous technology, is this technology much more efficient to use? An example that came to my mind as listening to the last speaker, Dr. Kresser, was the Dyna CT scan. All the benefits he talked about fitted perfect to this business model. In other words, created value, it reduced risk of using it, and it was more efficient. So most of the technology you see in the marketplace today has to meet these three criteria. If one of them is missing, it's not going to be technology. So that brings up a question is, what is innovation? There's a big difference between innovation and invention. Innovation is a process. Just remember that. It's a process by which you take an idea or invention and translate it into a goods or services that can be marketed and traded. That's innovation. If you have a great idea and it sits on a shelf somewhere, that's just an invention. It's not innovation. A lot of great companies have great inventions, but they were never able to transfer those inventions into innovations to be a successful product. Okay? But for that to happen, we got to understand how innovation happens. The way innovation happens is, it's not the right brain thinking or left brain thinking, things like that. It's all about one's cognitive ability of associating things. What do I mean by that? Is thinking differently, being creative. And the way you become creative is you connect seemingly unrelated ideas together. Seemingly unrelated, putting them together in unrelated ways, producing something novel or original. A good example of that would be Uber. Okay? Internet, 20 years, 25 years around, cab services for a long time. Somebody took these two concepts, put it all together with some platform technology, and voila, within a couple of years, a $60 billion company. Taking unrelated ideas and putting them together in unrelated ways to create something innovative. So every technology you see around you that's been developed usually is built upon some other technology that already exists, or combining that technology with something else. And we see that applied in our industry day in and day out. And it's true for every other industry. But it requires knowledge. The good thing about knowledge is it's everywhere around you. You just have to go acquire it. And when Dr. Lumsden talks about Pumps and Pipes conference, I think it's a perfect platform to acquire knowledge, because that's where you understand what other people are doing in their industries, how you can apply that technology to your industry and progress from there on. But the good thing about knowledge is, like I said, it's everywhere. You just have to go seek it. One of my basic advice to all my young engineers is never read journals only within your industry. Read journals outside your industry. Don't have to be an expert to it. Just understand what's out there, because you never know when you need it. Okay? And that's one of the fundamental things I advise every young engineers or scientist, everything. Explore your mind and acquire knowledge outside the industry. And a lot of times, the way we have seen innovation happens in my company is we put a team of very diverse individuals together of different backgrounds. Because if you have people with the same background in a group, you get the same solution. So diversity of gender, of knowledge is a fuel that drives innovation. Okay? So enough of innovation. Now let's shift gears. A lot of you guys might have heard about shale drilling, deep water drilling. Okay? Deep water drilling, or conventional drilling, has been around for a long time. But about 8 years back, there was a big boom in shale drilling because of technology that already existed for 60 years, but somebody figured out to combine two things together. That is horizontal drilling and fracking. And I'll briefly talk about that. This is a slide I'm showing, kind of a cartoon slide of shale drilling, because shale is a formation. Shale is a formation that is about a couple of 100 meters thick, but runs horizontally across the platform, the formation. The critical thing about shale drilling is you've got to position your well perfectly in the sweet zone and drill horizontally, keeping it centered within the formation before you can produce it. The reason I'm mentioning that is because This is where imaging becomes very critical as you're drilling the well. These wells are typically 8 to 10,000 feet deep, but they run across a long horizontal terrain at different levels. So positioning of your well is very critical. This is for shale drilling. But if we start looking at deep water drilling, it's a whole different thing. So before we start drilling, we got to understand your reservoir. A reservoir is a formation that holds the minerals. To us, that's our patient. We got to understand our patient, evaluate the patient before we can do anything. We got to understand the makeup of the patient. So this is what we call evaluation phase. It's to get a better understanding of the formation so we can get a maximum recovery from it. Okay? In other words, you got to first know your rock you're drilling in. Okay? Then you got to ask some critical questions as to how I'm going to tap into that particular rock. You got to get a critical insight of the reservoir itself. Because at the end of the day, you want to produce the maximum out of your reservoir. If I told you that the shale drilling, we're only able to recover 7 to 8% of what's down there. That tells me that we are leaving 92% of the oil behind. That's a substantial reserves. But we still don't have developed techniques to recover the 92%. Okay, so for that, you got to understand the reservoirs. That's what evaluation comes about. Once you identify the reservoir, you got to drill into it. You got to go ahead and use various techniques to go ahead and position your well at a sweet spot so you can produce the oil. And there's a lot of techniques going along with it. But here's an example of what we face as challenges. Here's a deep water well up in North Sea where you have the parent bore and then you branch out into multiple different directions to cover the maximum contact surface of the reservoir. I've taken the liberty of taking one of those wells and superimposing it on Manhattan. That gives you the feel of the depth and the vastness of what we're trying to explore. These wells are typically 25 to 30,000 feet deep, and they run miles together horizontally. Not 1 or 2 miles, but 5, 7 miles, or 10 miles. But the directional of drilling becomes very critical. And that's where imaging comes about. Okay? So for example, we have technology today that we can drill 30,000 feet deep, go 5 to 8 miles horizontally, and basically deliver the tip of the drill bit at a particular address we want to go to. That's the precision we are talking about. And while we are drilling, all that communication with the direction of the bit happens through pulses, through the mud column. Because when you're drilling something, you have to have a lubricant. You got to have a column of fluids that keeps the pressure in the formation so it doesn't cave in. Okay? So that's the kind of techniques we are talking about. For that, you got to understand the rock you're drilling in. Here's an example of how technology is advanced. Instead of drilling one well now, we can go from one particular platform and drill multiple wells in all different directions in a shale formation. And then we can frack it under high pressure and then produce oil from it. This is what we call as a factory approach to drilling. Previously, we used to drill one well at a time. But when the cost of it, when the price of oil came down dramatically, we had to change our manufacturing process, our production process. So we used our standard platform of how autos are manufactured. It's a platform-based approach. So here we take one rig and drill multiple wells, have another rig, drill multiple wells, and do basically a production line, you might call it, okay? But for that, you got to know your rock. Now this is a challenge we have in shale drilling. What happens is when you drill horizontally, you come to the formation you're interested in, but it's not continuous. It goes with fractures, it changes locations. So if you don't know where you're drilling, I don't have an image of where you're drilling, you might come down at the horizontally and you might drill through non-productive zones and you're wasting your time and energy. So basically you are taking a picture of the formation as you're drilling, And when you come to a fracture, you redirect your bit in a different direction to make sure you perfectly place your drill hole in a sweet spot. And that's where the imaging becomes very critical. These images are live that we are collecting, and we can maneuver our bit as it goes to the formation, so that way we can isolate or get away from dead zones that are not productive. Again, you cannot just do it blindly. You got to have some eyes and ears downhole at those depths to be able to take an image, communicate that image live to the surface, and be able to navigate your drill bit by sending it signals of what direction to go to be able to hit the sweet spot every time. This is where the power of imaging comes about. And all we are trying to do over here is we're trying to measure the total organic content of the rock, which tells you that that's where it all exists. Okay? So, the basic question to ask is, why formation evaluation is so critical? Because there are two basic writing business objectives. We want to obtain sufficient technical information for us to develop a business case to justify that this is a productive zone that will make enough oil to be profitable. And the second critical objective is to understand enough of the rock over its lifetime so we can get the maximum yield from it. Because in most of these wells, you have initial production and it decays very rapidly. So we got to develop techniques earlier on by understanding rock or how to go and model that particular formation so we can get a maximum yield out of the formation. Here's an example of taking an image. Here's a different formations you can see. The whole purpose of imaging is we want to be able to image the rock in small centimeter increments, so we can clearly understand the makeup of the rock, so we know which layers are producing zones and which one are not. Typically, oil reserve is not a big puddle of oil downhole. They put a straw in it and suck it out. These are all molecules that are dispersed through the entire rock over a million of years. And you tap in their formation and make those molecules flow in a particular direction, you can produce it. It's not as simple as putting a straw and just sucking all out. Okay? So the whole different science is involved, but it's measuring and imaging a rock at that macro scale to get an understanding of what it is. And this is where the different imaging techniques comes about. In the past, we used to have borehole resolution problems, but that's not a problem anymore, because we can basically look at the rock thousands of feet below and understand the makeup of the rock at a macro scale and have a clear image of what that rock looks like at that level. So like I said, the resolution is not critical. Here's an example of a map of the formation where it talks about where the potential oil may exist, where are fractures in the rock that you don't want to mess with, but it gives you an image of the formation. This is nothing but a 360-degree view of a borehole laid out flatly. So borehole imaging. A lot of these techniques may sound familiar. We have picked up a lot from medicine over the years. Basically, it's all about measuring the resistivity of the formation. That gives you understanding of the makeup of the formation. And we use ultrasonic methods, we look at density, and we look at the gamma ray techniques. And the way we convey our equipment downhole is two ways. One, it is run on wireline, which is nothing but a long electrical cable, which is driven by a motor, where you drop your tool and you log your well. When I say log my well, it is all about drilling a hole, maybe 12 inch in diameter, okay, which are called an exploration well. You take core samples from that particular well to understand the rock makeup, and you run your imaging tools that measures the profile and the composition of the rock to the entire length, so you have a good understanding of what the properties are in small increments. Okay, one way is we do it on wireline, which is a long cable where you drop the tool, and the other way we do it is, it's called LWD, which is a new technique. This is called logging while drilling. As we're drilling the exploration well, we're logging it at the same time. So we don't have to make a separate run to look at the makeup of the well. Okay, and I'm going to talk about that briefly. And the challenge we have is we have different fluids in the well when you drill it. Some fluids are water-based and some are oil-based. And each of them have different properties of conveying that signal to the rock. So we got to understand the makeup of the fluid if we can run imaging tools on it. So it's a different challenge. So in terms of using wireline, we have simple ways of doing it. Either we drop a tool which has a motor, takes a 360-degree image as it's running it. Or we can run a tool on pads which contact the borehole with sensors and they take an image. But with this particular technique, you have gaps in your data because you only collect information where the pads are running against the rock. But in this particular application, we have a 360-degree image on the tool. Other one, like I said, is measuring while drilling. This is the tool that is actually logging the well continuously as you run the tool and communicating the topographic and the details of the rock as you drill through it. Here's examples of how technology has evolved over the years. In 1960 was the first initial logging equipment developed, and now it's gone into a continuous logging while drilling, ultrasonic image, and you can see the complexity of the tools have been simplified, where now we just run a string, but the sensors are built into it that get in touch with the rock, and we measure the profile of the formation continuously to get a better example of it. Again, it's an example of how technology has evolved by using different ways of measuring resistivity of rock. So the measurements are recorded and basically looked at it on a flat sheet of paper, which is really the profile of the well circumference. Here's an example of what we are trying to do. This should not be any surprise to you. We basically send in a charge and we try to measure the resistivity of the rock. And these signals can go a couple of feet deep inside it, so we get a good understanding of what we are measuring. And then from that, we look at the profile of the well, and that will help us decide how we're going to produce that well. Here's an example of a map. When I was talking about using those pads while drilling, you see the gaps in the signals? These are the areas that have not been logged in. You can see that, okay? And then we look at fractures in the well bore. But the difference between this evaluation and this structure is, this was a little more sensitive from a static to dynamic image, but we saw a lot of sand composition, deposition, where we like to have areas that have clear layers of prehistoric formation, which tells us that that's where the oil reserves are. So now when we are producing it, we try to avoid sections like this, and we only treat sections like this to get a maximum yield of it. This is just an image of the formation. But when we talk about logging while drilling, which is the most recent technique, it's all about a complete instrumentation packaged in a drill pipe or a pipe with sensors built into it that takes a 360 measurement as you run the tool and you drill the well. Here's a very good example of LWD measurements. In this particular section of the rock, we see complex fracture relationships, okay? And we want to avoid fractures in the rock. And this particular example, you see very clear bedding of the formations that we want to focus on and not focus on fractures, because when you're injecting your fracking fluid, if it's a natural fractures, you lose a lot of fluids. It's like an aneurysm in artery. Okay, you want to avoid those sections because they just suck up resources and you don't get anything out of it. So you've got to understand the makeup of the formation as you're exploring it. And next technique is ultrasonic. We heard a lot of things ultrasonic. Yes, we picked up a technology from medicine, and we've been applying ultrasonic measurements for a long time in our industry also. Again, I don't want to go to the concepts ultrasonic. Most of you are very familiar with it. But with ultrasonic, we are measuring amplitude and travel time images. The reason we want to measure amplitude is because it gives you the makeup of the formation close to the wellbore. So for example, we can actually model the shape of the hole. Not all holes drilled are uniformly cylindrical because the formation is loose. It depends upon the pressures you maintain on it. Sometimes if you're overburdened, you can frag the formation. So you maintain a nice sweet spot when you're drilling, but you got to understand the profile of your wellbore. So that's another way we image it through ultrasound so we can see where the problem areas are. And last but not least, with the travel time of the signal, we can actually model the shape of the wall of the wellbore. The other important critical thing of imaging is from the geosciences. Geosciences is a technique or a branch of engineering that helps you actually model your entire reservoir depending upon the composition of the rock. Again, because when you model a reservoir, you're not only drilling in one spot, you may be drilling in multiple sweet spots to understand how do you drain the entire reservoir the most efficiently way and the most cost-effective way. So the properties and the imaging of the rocks also helps our scientists to build a comprehensive model of the reservoir so you have a better understanding of where to tap it and how to produce the wellbore. Here's a good example of a horizontal well. As you can see, the well path was defined, trying to avoid different planes and hit the sweet spot. And as you're drilling, you're measuring the composition of the well for its organic content. So now when you are fracking to produce the oil, you can avoid zones which are non-productive and focus on zones which have the potential of producing oil. Again, it's an efficient way of understanding what you're trying to do. 10, 15,000 feet, or sometimes as deep as 30,000 feet over a long horizontal section. Here's a good example of what a formation looks like in a horizontal well. Okay, where you can see multiple fracture zones. Okay, you want to clear beds of producing zones. You'll see a lot of sand dilution, but the formation was unstable. And you want to avoid these kind of sections in terms of when you treat the well to produce the oil. Again, imaging techniques extensively used in the energy industry to understand what goes on downhole. The other critical thing why imaging is important for us is to understand is we're trying to understand through the properties of the rock what the strength of the rock is. So as you're drilling the rock and you induce stresses in the rock, we don't want to break the rock. We want to maintain the stability of the rock. Because if you break the rock, then you're going to have a lot of depletion zones where you're going to have your natural resources getting sucked into it and not getting anything out of it. So this allows us to understand the stress planes of the rock for us to understand which direction we want to drill and which direction you want to frack so we don't damage the wellbore, get a maximum part of it. So we're trying to understand the horizontal stresses and the vertical stresses in the wellbore because this is how we achieve it from the images we take downhole. Here's a good example of an image taken where this particular crack was induced due to drilling. This is what you want to avoid. Here's a good example of how one of the wellbores was damaged, but it opened up. So now when you're pumping fluids to the wellbore, this particular area is sucking up all the resources. So we want to avoid that kind of damage to the wellbore. And if we know it ahead of time, we can take precautionary actions like running a special tool downhole and cementing this area off to prevent the leakage. Again, this is all about flow assurance. We struggle with the same problem every day. Okay, how to make sure that our pipelines and our wellbores are producing with no hindrance. But this is a good example of why imaging becomes so critical because You may be drilling in that well and not realizing it, what's happening, and all your resources in terms of drilling mud and fluids are getting leaked out into a formation and not being effective in maintaining the borehole stability. Another good example of understanding the reservoir is here's a vertical well that was drilled, and you map the entire depth of the formation, and you're looking at planes where are productive. For example, in upper zones, you see a lot of sand deposits. We like formations which are very well compacted and granular in nature. As you can see, layers by layer, very distinctive. This is a much more productive zone than this particular productive zone. And this is how, when we drill down and look at the formation, we can tell where do we stop, where do we produce, and which sections to leave alone. It's all about increasing productivity. So imaging techniques becomes very critical. And finally, here's an example of the imaging techniques do work. This poor guy was, I don't know how he ended up in, it was a water-based mud, and this guy was buried at about 400 meters deep. Okay? And he got picked up on one of the imaging techniques. But this kind of gives you a little bit understanding of how different imaging technologies are used across different industries. And I could spend another hour or so talking about just our pipeline inspection equipment. These are imaging techniques we use of inspecting flows in pipelines, which runs thousands and thousands of miles. And these are what we call them pigs. These are big, large equipment we drop in the pipeline, and they run or get pumped to the entire end of the pipeline, taking images of the pipe to look at flaws or cracks or erosion, so we can take preemptive corrective actions. So the technology can be applied in multiple different fashions. We continuously explore and exchange ideas with different industries to understand how they are used. And I think the one that caught my attention this morning was the dynamic CT, okay? Because the things we do, we like to acquire information in a very dynamic way. The biggest constraint we have in terms of collecting information is because we transfer information to mud pulses, and the communication rate is very slow. We have tried to develop pipes that are fully wired with fiber optics, but when you have a wired pipe, as you make connections, it becomes long and tedious process, and a slight break in the connection, you lose connectivity. So right now, today, we are developing techniques of communicating through the mud column, through acoustic sound pulses, that we can downhole information so we know real time where we are, how we position ourselves. Okay? Again, thanks for the opportunity, and hope this was informative.
So let me explain what he's talking about, mud pulsing. It'd be like using an atherectomy catheter and transmitting signals back through the blood that we measure. We use the blood as a means of passing information. We have blood vessels that are blocked off, and we just basically try to jam tubes through them, and sometimes they don't work, and we have no idea what the occlusion is made of. You would never dream of doing it. We said to you, basically, how much does it cost to put an exploration well down in the Gulf of Mexico? Oh, my God. A day.
I mean, especially in the Gulf, things are very, very expensive. You know, I always tell people that imagine you are developing a reservoir. It takes 15 years to develop it, $12 billion of investment before you produce the first barrel of oil. It's a risky business. Yeah. But unconventional and shale energy is fast.
Yeah.
It's very fast.
So let me ask one other thing, is that I used to think that when you showed all these holes in the ground, it was just a hole in the ground. But it's not. You line it.
Oh, yeah.
So explain how you line it, because to me this is like a branched endograft that's in there. These things are lined from top for miles and miles, not just a hole. You drill a hole in the bottom, oil's there, and it comes out the surface. It comes up and disappears out the next formation that's got porosity, so they have to cover this.
Now, the way we drill a well is, if it depends on the depth of the well, we start with, say, 36 inches in diameter. Drill it about a couple hundred feet. We cement it in with a casing. Casing is a metal pipe that's between a bore and the ID, and you cement around it. Then you hang another section of the pipe or casing and drill another 5,000 feet. We cement that in. And you keep on drilling is we go down up to 30,000 feet deep
So
with
how
pipes.
do you put in the side branches?
What's that?
How do you join them together when you've got a multilateral well?
Well, that's a whole different technique, because once you drill a well and you cement it into place, then we have special tools that we can deviate the drill and cut through the pipe and drill a lateral. And we cement that lateral, and we create junctions where if you want to go to leg 1, leg 2, or leg 3, that particular junction is designed such that it allows you to decide which branch you want to get in selectively. Okay, so that's the way we cover a lot of area, especially on a deep water well. Moving a deep water rig to a different location is very expensive. So from one rig, we can drill 24, 30 different wells in different directions, trying to get a maximum contact with the reservoir to get the maximum production. Okay, and each of these laterals has to be navigated perfectly to hit the spit spot. And that's where directional drilling technique is so critical of understanding where your bit is moving, knowing the formation you're drilling into it, and modeling it at the same time as you're drilling it.
So two final questions. How do you navigate them? How do you know where you're going?
What we have is, we have a drill bit with different sensors that measures in 3 dimensions the location of the drill bit. And depending upon the orientation of the drill bit, if you want to move it left, we have a tool with 3 pads on it that pushes against the formation. Just like driving, if I want to take the bit and move in this direction, I put more force on this side of the well bore, it forces the bit to go in a different direction. Okay, it's a continuous signal of applying pressure of navigating a drill bit continuously. Okay, so again, it's a whole different science, but it's done continuously. That's the key thing.
Thank you, sir. Could listen to you talking about these things all day. I think you got the raptor here. Appreciate it very much. Thank you.